I know that we're going to be talking about metal capacitors. I just have to figure out where in my hodgepodge of notes that I wrote originally that follows the textbook pretty linearly did I. Okay. Stylus, there we go. Metal capacitors. So it should not be an overwhelmingly unobvious thing that if you have the ability to put them on each other, you can form capacitors using the metal layers as well. So that could be something as simple as this, where we have our substrate. Here we have our field oxide layer, where our polysilicon layers effectively reside. And then atop that, we could put some section of metal 1. Scaring me by joining on Zoom too, Sam. I'm sorry. It's okay. Yeah, not a problem. And then here would be our metal 2 layer. And in a situation like this, obviously we're forming some intended capacitance, which I'm going to call CM2 to M1. But additionally, we get a parasitic capacitance between our lowest metal layer and our substrate. So a couple of things that we need to talk about here with regards to these metal capacitors, okay? The math involved is effectively going to be the exact same thing as we did with the poly 2 capacitor. However, we are typically going to get significantly smaller capacitances. The reason why we are going to get smaller capacitances is because the distance between the metal layers is significantly greater than the distance between the polysilicon layers, okay? We also get a smaller bottom plate capacitance because our bottom plate, or the lowest level, which is metal 1 in this case, is significantly further away from the substrate than the poly 1 layer was as well. Okay. So if we wanted a metal 1 to metal 2 capacitor, formed with 100 micron by 100 micron metal plates, how does the bottom plate capacitance compare to the design capacitor value? And obviously we're going to be using our table here. Excuse me. So our design capacitor between the metal 1 and metal 2 layers is going to be the capacitance, the area capacitance between the metal 2 and metal 1 layers per unit area times the area of our plates. And then we're also going to have a fringe component times the perimeter of our plates. And so from the table, I believe that I provided you guys, it should be 33 attofarads per micron square of capacitance between the metal 2 and metal 1 layers. Yeah. And then the fringe capacitance should be 47 attofarads per micron. I think I left my table upstairs, but it's not like I couldn't pull it up. And so we get a designed capacitance of 348.8 femtofarads. For our bottom plate capacitor, we're going to have something extremely similar, right? We're going to have a contribution from the capacitor area as well as a contribution from the fringe field. So this is going to be metal 1 sub times 100 microns squared plus, sorry, 400 microns. From our table here, we get 28 attofarads per micron squared. And 51 attofarads per micron times 400 microns. And before we do a calculation here, let's compare these numbers, right? So obviously the size of the plates is the same. The perimeter of the plates didn't change between the designed capacitor and the parasitic capacitance, okay? But the, let me kill my email or things are gonna keep popping up and it's gonna drive me insane. The thing here that I'm really trying to point out is that the capacitance per unit area between metal 2 and metal 1 is extremely close to the capacitance per unit area between metal 1 and the substrate. Similarly, like that's true for the area capacitance figure and the fringe capacitance figure. So if we do the math here, what we'll find is that our parasitic capacitance is 300.4 femtofarads. And so this number is 86.12% of our designed capacitance. Okay. Very, very significant, right? So the poly 1 to poly 2 capacitor that we dealt with earlier, which was fairly small, we had about a 16 to 17% parasitic versus as compared to the design capacitor. Here in these metal capacitors, it's almost a 1-to-1 ratio, okay? So if for whatever reason we really, really need to use the metal layers to form a capacitor, there is a technology that we can utilize, but it requires at least 3 metal layers to do it, which luckily enough for us, our technology node has 3 metal layers. So what I'm about to draw is what I'm going to call a folded capacitor, okay? So we have our substrate, and then our field oxide layer. On top of our field oxide layer, we are going to have our metal 1 layer. Do it like this. And just to make things a little easier to draw, up here is where our metal 2 layer is going to exist. Like so. And up here is going to be where our metal 3 layer will exist. And effectively what we're doing is we're making kind of a stylized capacitor sandwich, but we need to make sure that we have a connection between the various layers. So on the metal 2 layer right here, I'm going to give myself a small amount of metal so that I can literally connect my top plate down to this, this metal 3 plate down to the metal 1 plate, so that I have some capacitance between here and here, C metal 1 to metal 2, electrically in parallel to C metal 2, metal 3. Only the metal 1 layer is going to contribute to the parasitic capacitance that we see, right? Because there's going to be metal in the way. We might have some fringe that we might have to worry about, but we're not going to have to take into account any area contribution from metal 3 all the way down to our substrate. So this is significantly going to increase our designed capacitance while keeping our parasitic capacitance effectively at a constant value. So this is a structure that we can utilize. That being said, poly-poly is probably your better way to go the overwhelming majority of the time. All right, so now that we know about metal capacitors and polycapacitors, we need to pay attention to parasitic capacitances that can form whenever we are connecting metal layers to our polycapacitors to serve as electrodes. So what I mean by that specifically is, let's say that we have the following structure. Here's our substrate, our field oxide layer, and then I believe this is the color that I've been using for our poly layer. So something like this. And then this red bit right here is poly 2. That line was supposed to be black, but it will be okay. I'll just redraw it. And then up here, we have a run of metal 1 that we're going to use the contact layer to make contact with the poly 1 layer. And then over here on the right hand side, we're also going to have a run of metal 1 to make contact to the poly 2 layer. So up to this point, we know about our poly-poly capacitance. So C poly to poly 2. We know about our bottom plate capacitance between C, poly, and sub. But we are also going to have this capacitance between metal 1 and our substrate. And we are going to have, I'm going to put a single prime here, and we're going to have this capacitance also between metal 1 and substrate. And I'm putting primes because they might have different areas and all that kind of good stuff. So electrically, what are these things going to do, right? We have more parasitic capacitances that have snuck their way into our design. So the capacitance on the left CM1 dash sub with a single prime is electrically in parallel with C poly sub, our bottom plate parasitic capacitance, right? The C double prime M1 sub is connected to our top plate and our substrate. So it's depends on how other things are connected effectively as to where it's going to show up in parallel with. But generally speaking, these parasitic capacitances between the metal layers and the substrate are going to enhance the effects of the bottom plate capacitance more so than they are going to enhance the effects of the designed capacitance. So these are just some of the things that we need to be aware of. I believe in your exam, I give you, I think, a poly plate that looks like the letter E or something like that with metal runs and all that kind of stuff, and ask you to calculate all of the various different capacitances that are going to show up there. So I just wanted to make sure that we've talked about the other parasitics that are going to show up. So really, anytime you have metal directly over substrate, you're going to have a capacitance. Anytime you have poly directly over substrate, you have a capacitance. Anytime you have poly over poly, you have a capacitance. Anytime you have metal over metal, you have a capacitance. And theoretically, you could have metal over poly, which would also give you some sort of capacitance. So there are lots of parasitics that can show up that you need to be cognizant of. So for this guy right here, I would argue that there aren't any metal poly capacitance. And so what I mean by that specifically is that the metal one layer, so let's put a slice here, right? The edge of the metal one layer does not overlap poly 2. Where it overlaps poly 1, they are electrically connected together by that contact. So there isn't a capacitance, there's a small resistance between those two different portions of the capacitor. And you see the same thing effectively on the right-hand side. Now, that being said, I do see something here that is potential, what you are indicating, or this may be what you're indicating. This little guy right here is a capacitance between the metal one layer and the poly layer, which is parasitic, but would actually show up in parallel with the design capacitance. Right. So I neglected that.
Yes, but
Yeah, it's that part's going to be pretty small, assuming that you are designing your capacitors such that your poly 1 plate is as small as it can possibly be to accommodate your poly 2 plate, which is generally going to be the case because the larger you make your poly 1 plate, the larger your bottom plate parasitic capacitance is. So there will be some small contribution there, but I would argue that it's probably not going to be. Yeah, like you could calculate it, and I bet it'd be somewhere on the order of 5%-ish, depending on how wide you made your run and all that kind of stuff. But when you're talking about a bottom plate capacitance that's always going to be at least 10% plus, the larger you make your capacitor, the larger that is, and then taking into account all of the contributions of the other things that are compiling on top of that because they show up as electrically in parallel. You're right, yeah. Like, it is a thing.
yeah. It's important to know.
There might be merit in calculating it, but I would not expect it to significantly influence the behavior of your device as much as the cumulative effects of the other parasitic capacitance as well. All right, so I think we have beaten the different ways that we can implement resistances and the different ways that we can implement capacitances kind of to death. So let's talk about something different and really kind of wrap up this section, okay? So this is what's covered in largely in chapter 5, and we're going to gloss over the parts that we've already covered from chapter 5 while talking about the different ways we can implement these things, okay? And so what we're going to be talking about right now is the temperature coefficient of resistance. So getting back to basics, resistivity, I'm misspelling it, is a material property that determines how difficult it is to pass current through an object. In your solid state electronics class and revisited in your analog electronics class, you learned that mathematically resistivity rho E for electrical resistivity is given by 1 over Q, the elementary charge or the charge of an electron, mu n times n plus mu p times p. Before we get too far here, for those of you that have had 335 and 336 recently, did I use P as subscript for holes or H for subscript as holes? I feel like I used P.
Yeah, I think
Okay.
because I think that's also what's used in solid state, right?
Okay, I just want to make sure because different textbooks use different things and some of my notes from some classes have H and others have P. Sometimes I have mu E for electrons and sometimes I have mu N for electrons. So I'm just trying to be consistent, at least with the same students coming up through all these classes, so that they have some idea of how this stuff all interrelates. Okay. So just as a basic recap here, I'll do all this stuff in blue. Q is 1.6 times 10 to the minus 19 coulombs, our fundamental charge. Mu n is our electron mobility, measured in centimeters squared per volt seconds. N is our electron concentration, measured in electrons per cubic centimeter. Mu p is our hole mobility, measured also in centimeters squared per volt seconds. And P is our hole concentration. I thought I turned you off email. Why are I still getting messages? What is this thing? Close that. Discard. Concentration. Hole, so H plus per cubic centimeter. Okay. Which of these quantities depend on temperature? Anything else? The answer is literally everything but Q, which is a fundamental constant everywhere. The mobilities are absolutely temperature dependent, and the electron concentrations are also absolutely temperature dependent, okay? So how these things trend is that mu n and mu p tend to decrease as temperature increases. So our mobilities go down the hotter our crystal gets. This is because as the hotter our crystal gets, the more lattice vibrations occur. And so we have more scattering events. Effectively, it's easier for free charge carriers to run into the vibrating atoms, okay? Since the carrier velocity or the average carrier velocity decreases because there are more scattering events, our mobility is decreased. Okay? But N and P tend to increase as temperature increases. That additional interatomic vibration makes it slightly easier for bonds to break, releasing free charge carriers into the bulk of the crystal. Okay. So as the temperature increases, we see an increase in the thermal generation of electron hole pairs. Electrons are moving from the valence band to the conduction band, leaving behind holes, which again is just the definition of electron hole pair generation. Okay. So the temperature coefficient of resistance for a material depends on which of these two counter trending things is the dominant mechanism, right? So if mobility is the dominant effect on the resistivity of a material, the material will have a positive temperature coefficient of resistance, which we call TCR. If the carrier concentration is the dominant effect on resistivity, the material will have a negative temperature coefficient. So way back when you guys were freshmen with your thermistors, those were negative temperature coefficient devices. So like if you had a thermistor that was, when you had your thermistor, you used it in a simple voltage divider circuit, and I believe the thermistor was at the bottom part of your voltage divider. If you had had a positive temperature coefficient thermistor, it would have needed to go as the top branch in your voltage divider circuit to effectively get the same trending things that you want, where you would see the voltage increases as the temperature increases using your little sensor, okay? So all of that to say, this is actually something that you've dealt with very slightly 4 years ago before, but it's not entirely new. Okay, so let's write that down. So when mobility is the dominant effect on resistivity, the material will have a positive temperature coefficient of resistance. And I'm calling this parameter TCR1. TCR is obviously stands for temperature coefficient of resistance. 1 comes about because we're only looking at this on a first order level, effectively. So if we were to do a Taylor series expansion effectively, that governs how this thing actually behaves, we're throwing away everything after the first deal, because that amount of math is unnecessary for us to figure out how this thing trends, okay? So from this, we can see that as temperature increases, electrical resistivity increases when mobility is the dominant effect. When carrier concentration is the dominant effect, on resistivity, the material will have a negative TCR1. So in this case, as temperature increases, electrical resistance decreases. Okay. So in general, for a silicon-based device, we get a curve that looks something like this. So our horizontal axis is temperature measured in degrees Celsius or Kelvin. Our y-axis is the resistance as a function of temperature. And what we get is a pretty simple linear relationship. Something like this, where indicators like this. So at this critical temperature T0, we have some specific resistance, which we are going to call R of T0. And this thing has a slope that is change in resistance over temperature, so that we can say R as a function of temperature is R times T0 multiplied by 1 plus 1 over R T0 times delta R over delta T times T minus T0. I know this is getting ridiculous. This guy right here, 1 over R times the change in resistance over the change in temperature, or temperature coefficient of resistance. So effectively, if we know how this behaves at some specific temperature, like room temperature, and we know what the temperature coefficient of resistance is, we can estimate what the resistance is at other temperatures, right? So if we have say N-well material has a temperature coefficient of resistance of approximately 2,400 parts per million per degrees Celsius, or a 10 kilo ohm N-well at T is equal to 27 degrees C, room temperature. For a 10 kilo ohm N well resistor, determine the variation in R as T ranges from 0 degrees C to 100 degrees C. Okay. So R at 0 Celsius is going to be the nominal resistor value, 10 kilo ohms, times 1 plus our temperature coefficient of resistance. So 2,400 parts per million. I have this as 0.0024. 2,400 parts per million is 2.4 parts per thousand. Okay, that's why it makes sense. Sorry, I was making sure the decimal places are correct. Yeah. So 2,400 over 1 million is literally 0.0024. Okay. Nope, I had to double check it too. So, and then we have our temperature of interest, which is 0 degrees, minus our reference temperature of T naught, which is 27 degrees. And this comes out to be 9.352 kiloohms. At the opposite end of the spectrum, for 100 degrees Celsius, this is going to be 10 kiloohms times 1 plus that same coefficient. 100 minus 27, and we get 11.752 kiloohms. Okay, so I'm trying to remember if and where in my notes I have this, and it doesn't look like if I wrote it down, I brought it with me. Let's talk about the stability here briefly, okay? So for an N-well type material, the temperature coefficient of resistance is 2,400 parts per million. And so we see that for a 100 degrees Celsius temperature variation, we have approximately 2,500 ohms worth of variance, right? So it's 650 ohms variance when we're lower than our reference temperature, and it's 1.752 kiloohms when we're higher than our reference temperature, but our reference temperature isn't really in the middle, so it's not a true weighted type thing, okay? But there's a pretty large amount of variance within a relatively standard operating range for an electronic device, okay? Typically speaking, you probably wouldn't try to operate modern electronics as low as freezing or as high as the boiling point of water, but as any of us who play video games and all that kind of stuff know, there's definitely been times we've got our video card pushing that 100 degrees C mark, as opposed to operating it at room temperature where we would like it to be, or cooling it even lower than that using some sort of liquid cooling or some kind of thing. So we can see a relatively large amount of variance in this particular resistance. Now, other materials like active material or high-res poly 2 have different temperature coefficients of resistance. So creating resistors out of those other materials tends to add complexity to the process, like literally the processing that occurs in the creation of your device, which costs a little bit more money, but you also typically get better resistor stability as well. So it behaves better under that same temperature range. So I'm making this number up off the top of my head because I cannot remember it, but I believe that the temperature coefficient of resistance for high-res poly is measured in parts per billion, not parts per million, okay? So it's significantly more stable due to temperature variations. Yet another reason to use it. All right, now let's talk about the voltage coefficient of resistance. And we've touched on this slightly, but we'll give it a more formal treatment. So where this voltage coefficient of resistance, or where it's most obviously seen, is if we were to look again at an N-well resistor, where our well, I think, was defined in purple, so that's what I'm going with here. And desperately need to develop PowerPoints for this stuff. If we were to put 5 volts on one side of this N well and ground on the other side of this N well, we have discussed this previously. We have some form of depletion capacitance. And so our space charge layer on the unbiased side is actually skinnier than the space charge layer on the biased side of the PN junction. Drawing it exaggeratedly here. Something like this. So this particular device exhibits a voltage coefficient of resistance because the resistance of the material changes as the voltage across the that's applied across the device changes. Okay, in this case, it's due to the thickness of the N well's variance over its length. So we see that as the reverse bias voltage increases, the average resistance of the N well increases. This relationship is given by voltage coefficient of resistance, VCR, is 1 over the resistance at some nominal voltage V naught times delta R over delta V. Very, very similar in definition to our temperature coefficient of resistance. And then our resistance overall as a function of voltage is pretty much the exact same equation. R of V naught, our reference value, times 1 plus VCR times V minus V naught. The resistance increase due to the voltage coefficient of resistance is typically smaller than the temperature, the effects due to temperature coefficient of resistance. So this is reasonably small for an N-well type device, but it is there. And as we get into other materials, it's even less. Okay. All right, so I'm missing a page of notes here. No, okay. Last thing we're going to talk about here, just very, very briefly. Capacitors also exhibit voltage coefficient and a temperature coefficient. Okay, so for capacitors, the temperature coefficient of capacitance, we have C of T naught times 1 plus TCC times T minus T naught, where the temperature coefficient of capacitance is 1 over C times the change in capacitance over the change in temperature. I'll put this as a simple note here. Approximately 20 parts per million per degree C for poly to poly 2 capacitors. And then we have capacitance as a function of voltage, which is again practically the exact same expression. VCC minus V naught, where VCC, excuse me, is equal to 1 over C delta C by delta V. And this is approximately 10 parts per million per degree C or poly to poly 2 capacitors. And it's hundreds, if not thousands of parts per million when we're dealing with metal capacitors. So poly to poly 2 capacitors are more expensive, but they're the most stable capacitors that we can make. Similarly, high res poly 2 resistors are also the most stable, but also the most expensive in terms of processing cost and time resistances that we can make. So there's always a trade-off here between performance and cost that we are going to see in these devices. So there's merit in actually making things using the other layers if it's not performing critical functions. All right, I think that's enough out of me for today. So the next notes that I have here very explicitly in my binder are related to the formation of transistors and things like that. So I am trying to make a decision. I have my matching in analog components notes literally just tucked into my binder in no specific place. And I'm trying to decide whether or not to teach matching components before I teach transistors and all the stuff that's associated with them. So herein lies the conundrum. Explaining how resistors and things like that are matched is pretty straightforward. Which means, since we've covered resistors and capacitors to death at this point, it seems like a good point to talk about how we would match things to make sure that we're getting the behavior that we want. That being said, it is important that we also understand how transistors are matched as well. It's the same techniques that is employed using matching resistances and capacitances, but it is not nearly as obvious as to how it's actually carried out. So, any thoughts? Everybody's just shaking their head. All right, so I guess that means I just have to figure out how to do my job by Friday. All righty, that's what we'll go with. Okay, so that's fair. So we'll talk about, so matching largely relies, or the generally accepted technique is what's called a common centroid matching technique. And for any, I know that means next to nothing for you. For a two-terminal device, explaining how that works is fairly straightforward. For a three-terminal device, it gets wonky fast. So what I will very likely do is we'll talk about matching for resistors and capacitors and all that kind of stuff in our next class meeting. Probably start introducing some of the layout aspects of transistors at our next meeting. And then I will show you a layout of how transistors are matched with little explanation because it's just odd looking. But effectively, it's utilizing the physical positioning of different parts so that there is a common centroid. And I know that means nothing to you right now, but hopefully within 10 minutes of Friday's class, it will have some meaning. So, all right, that seems like as good of a plan as any. So thank you for the suggestion, Sam.